How do people learn about and represent complex functional structure? For example, when they're trying to figure out if and when Last Christmas will be played in the radio this year. We tried and assessed this question by using a Gaussian process approach towards learning functional structure. This results into 3 different proposals of how structure might be encoded. The first proposal is the radial basis function kernel, which is mostly agnostic about the underlying structure. The spectral mixture kernel learns about structure implicitly based on the fact that every stationary kernel can be expressed as a spectral density and then capturing this density by a mixture of Gaussians. The compositional structure search approach we put forward assumes that structure is described explicitly by a combination of simpler parts. We formalize this intuition by a grammar of different kernels, which are the linear, the radial basis function, and the periodic kernel. These kernels can be combined by either adding or multiplying them. In the first experiment, we sampled functions from a compositional kernel and let all of the 3 proposals produce pattern completions given a learning set, and then just made participants choose between the different completions. We found that participants strongly prefer compositional completions in the first experiment, and that this also holds true in the second experiment where we sampled the ground truth from a spectral mixture kernel. Using Monte Carlo Markov chain with people, we let the compositional kernel approach sample different completions and ask participants to either accept or reject them, thereby assessing their subjective posterior over different predictive components. When the ground truth came again from a compositional kernel, participants reliably converged to the combinations that had generated the functions. In a second experiment, when we used real-world data, participants converged to common combinations found in the Gaussian process literature. Next, we let participants draw predictive lines into noisy realizations of functions that we had sampled from a compositional kernel. Again, we found that the compositional kernel corresponded more closely to predictions of the participants than the other 2 approaches, which hold true for both inter- and extrapolation judgments. Finally, we asked participants to judge about how well they thought they could predict different functions that we had sampled from either the spectral mixture or the compositional kernel. Here we found that compositional functions were assessed on average to be more predictable, and that this holds true for both single and comparative judgments. In conclusion, we have found that the compositional approach towards structural learning is a powerful yet elegant way to explain how humans perceive and treat different functions. Our empirical data shows that they do so by exhibiting a compositional inductive bias over different structure. In the future, we want to assess other cognitive domains such as how people, for example, remember functions or how they detect change in functions. Thank you for listening, and please come to our post on Monday.